Good. Okay, last hour, number 20, I believe. Application. Not in the sense of technology. We haven't any technology based on this yet. But I want to make this a little bit more concrete to show you how, in one particular case, one can take all this and try to do some physics with it. Because a theory is good if you can compute with it and tell you something that happens in the world. This is not a fully completed, fully understood application. It's to some extent work in progress. It's not clear if the first results are solid enough to be considered final. Maybe they will evolve. There are various reasons for which they could still evolve. A number of things are not yet clear. But what is good is that you can see how this machine built this theory can be used concretely for, you want chocolate? This one?
I will add a comment.
Tommaso wants chocolate. And you're going to see how this could be used, because otherwise, I mean, unless we go to some real physics, this becomes just juggling with ideas and so where are the cases where we can use the theory? Where, well, in the cases where quantum gravitational phenomena are not negligible, and the two typical ones are the early universe and black holes. It's not obvious that these are the only ones. There could be others, right? It could be some astrophysical phenomenon where something happens, maybe even some laboratory thing, who knows, at some point. But for the moment, these are the only two cases where clearly we need quantum gravity to see what happened. Cosmology, there is a huge literature of application of loop quantum gravity, both in this form and much more in the canonical formalism, in which the kinematics is exactly this one, but the dynamics is given directly in terms of a Hamiltonian Wheeler-DeWitt equation rather than in terms of amplitudes. Big literature. I'm not talking about that. Black holes, there's also quite a literature in loop quantum gravity, and from various perspectives. I want to just focus on one calculation, which is meant to try to understand what happens to black holes in the region where we don't know what happens, using this machine here. So let me start. So application black hole. Black holes. So there's things we know very well about black holes, because black holes seem to be perfectly well described by general relativity as far as we can measure about them, including strong field regime with recent measurements. So the horizon of a black hole is pretty well described by GR as far as we see, and we have no reason to suspect that when you go in, it's also well described by GR. Where we get lost is when R equals 0. We have no idea what happened. So you throw something, a black hole, goes in, cross horizon, why not? Goes to R equals 0, and then what? We don't know. And the distant future of a black hole. So you put a black hole here, it forms, a star collapsed, you wait, and then what? There is a very credible calculation by Hawking and repeated by so many ways that is very plausible, that the black hole shrinks because of the back reaction of the Hawking radiation. So there's quantum fields around. These quantum fields have particle production because of standard particle production in curved space-time. So there's a negative energy flux that falls in, and there's a back reaction to the classical geometry. So the black hole shrinks. So this is never observed, of course, but very plausible. The black holes become small, and then nobody knows. people wave hands saying, well, it pops into nothing, but that doesn't mean anything. We don't know. We need quantum gravity. So the phenomenon we want to study, let me first do a sort of a cartoon. We have a star. This star, so this is a star. The star collapses. This is time, in some sense. And an horizon form. So let's do horizons in blue. The horizon form. So here is a black hole. We are sitting here watching this. We see a black hole. And then presumably this shrinks. This is not clear what happens at all. So there's a big question mark here. What happened here at the end? It maybe dissipates. Well, what are we going to see if we're here? And there's another big question mark in the central singularity at r equals 0. Another big question mark. What happened here? We don't know. So this picture is it's very confusing. In this picture, the light cones are sort of like that, right? Because the horizon is a null surface, so all time like go in, which means that this horizon is actually the future of anything which is inside. So this is not a good picture in the sense that this seems a space like singularity, but it's really a time-less singularity. It's really in the future or something. When you go there, it's in your future, not on your side. You cannot avoid it. So the question is what happens here and what happened here. In the terminology that I like to use, this is region B and this is region A. So region A is everything around the central singularity. Region B is whatever happened at the end of the evaporation. Maybe they connected. This is what we don't know. Meaning, we seem to understand very well all the physics around. So we think that the equation we have predict something plausible, but we have no idea what happened there. Okay, so we want to use quantum gravity for that. So let me redraw this picture in a little bit more relativistic way. So let's do it in a Carter-Penrose diagram, namely putting the light rays at 45 degrees, and I get the standard picture of a black hole forming, a star collapsing. So this is the blue line. The star here is the center. This is the center. This is r equals 0. So the star collapses, enter its horizon, and falls in, and that's the singularity. This is past null infinity. This is future null infinity. This is spatial infinity. This is future infinity. I can either stay all the way outside the black hole or fall inside the black hole. If I fall inside the black hole, I necessarily hit the singularity. If I go at the speed of light, I go out in one of this direction here. So if I shine light, it goes out here. Every light coming in comes from here. So region A, where we don't know, is this one. And region B, where we don't know, is this one. Is a distant future. So we don't know what happened falling into the singularity, and when we don't know what happened there, which means that we need quantum gravity to go there. Whatever happened, so in other words, don't take this picture seriously as a physical prediction, because we really know nothing about there, right? So this picture has to be cut here. So this is a fantasy. It's like, dragon of Game of Thrones. It's not true. Beautiful, but not true, because generativity is not reliable there. whatever happened in the future, it's reasonable to expect that in the future, at some point, there's just a regular space-time after the full evaporation of the black holes. In the distant future, there should be a regular space-time. So one other way of viewing this is to think that this is the beginning of the story. And there is an end of the story, which is still a space-time with a sort of normal causal structure, and this story happens here at some point. This is four black holes collapse, evaporate, explode. So the entire story is in this region here, and in the rest of the universe, which is large and infinite, nothing happens. So we might imagine that the rest of the universe is described by a standard causal diagram, and this is the quantum story. Okay, so let's say that there is a quantum region, which is what we want to understand, which is sort of here, which is the A region and the B region, which are there, and we know that from classical general relativity that the star which is collapsed to produce this quantum region here, the high curvature for this quantum region, has created an horizon which goes there. And in fact, there is a conjecture due to Penrose, I believe, which is called the cosmological censorship conjecture, which says that every time you have a singularity in classical GR, is most likely it's always, that's a conjecture, inside hidden inside an horizon. Okay, and it seems to be true up to perhaps some very strange things. So let me believe for a moment it's true. If it is true, general relativity is invariant under time reversal. So its opposite is also true. So if you look from the future back, to go to the putative singular region, which is a quantum gravity region here, it's likely that you're also closed by an horizon. Right? So that's a likely picture of what happened. Namely, you have a classical metric here. You have a classical horizon. You have the inside of a black hole. You have another horizon here. It's also classical. You have a quantum transition in between. Okay? And that's what we want to explore, whether this can happen and how this can happen and whether this happens. For doing this, we need two things. We need a classical description of whatever is around here, and we need a quantum description of what happens here. But notice that the to do this quantum description of that, what we need is exactly what loop quantum gravity gives us. Namely, we have a classical geometry. They're closed inside a surface. We can choose arbitrarily because we can always remember Wigner discussion of a quantum system. If you have a quantum system, you can choose your boundary between the quantum system and the classical system the way you want. The probability are going to be the same. You can always move your boundary out. So there is a freedom. You can take pieces of your apparatus and consider them quantum, and the final probability are the same. So you can close this inside a boundary. This is a space-like surface. This is a space-like surface. You have a classical geometry here, classical geometry here, and you need some theory that tells you about how you go from some classical geometry to a classical geometry and compute amplitudes for that, and that's exactly how loop quantum gravity is formulated. Okay? So to study this phenomenon, the project is first study the metric outside, the outside metric. So everything outside this red three-dimensional surface. And then from that, compute the metric of the three-dimensional surface. Let's give it a name, sigma. sigma down, sigma up, sigma minus, sigma plus. Okay? And then forget all the rest, and now you can compute the probability amplitude of that, and you'll see how we connect to observations, at least in principle. And you can use loop quantum gravity to do the amplitudes. And to do that, loop quantum gravity is formulating truncations. So you have to truncate the theory, presumably what tunnels from here to here. Why is it tunneling? Because there's no classical transition from here to there. Classically, you just fall into the singularity and the theory dies. So there should be some non-classical evolution from here to there. So some quantum evolution, that's tunneling. The quantum theory is giving you this tunneling, and to presumably the degrees of freedom that are tunneling are not arbitrary small degrees of freedom, are the degrees of freedom in which of the size of this phenomenon, the size of the black hole, the size of this length, time here, whatever is. So you want to truncate the theory, doing a discretization of sigma and the interior region. Let's call the interior region R. And so this is an R. Sigma is a three-dimensional thing. R is a four-dimensional thing. The region inside, and then use quantum theory. And how do you use quantum theory? Well, if you know the geometry inside, you know the geometry of sigma. So geometry outside. So you know the geometry of sigma, and you know, careful, you know not only the metric but also the extrinsic curvature. So the intrinsic and extrinsic curvature of sigma, because you have the full thing, you know how. So more than the metric, I should say the geometry of sigma, intrinsic and extrinsic. And now you have the intrinsic and extrinsic geometry of a discretization of sigma. You can write an extrinsic coherent state in the Hilbert space of loop quantum gravity truncated to the truncation you have. So you can write a coherent state with this intrinsic and extrinsic geometry here and here. And once you have the state, you can compute the amplitude. And see if you can learn something about that. So let's refine a little bit this scheme and get something a little bit more precise. Starting from point 1, the geometry outside. If you're a good relativist, the first time you see this, you say, well, there is no geometry outside possible here, because this is a black hole. This is an horizon inside the black hole. This is its time reversal. This is a white hole. This is the horizon of a white hole. So here you have inside the falling star or whatever comes out here. I don't know, but outside a spherically symmetric. We know the metric outside. Here is Schwarzschild. Okay, so here it has been Schwarzschild. Here it has been Schwarzschild. And we know that Schwarzschild continued in a black hole. We also know that Schwarzschild continued in a white hole. But the extension of Schwarzschild to a black hole and a white hole, this is a black hole, this is the white hole, this is the external Schwarzschild. The white hole in the past and the black hole is the future, not the other way around. The black hole in the past, the white hole in the future. So this seems impossible, but in fact it is possible, because you can build a metric all around here, which is locally isomorphic to Kruskal, to extend the Schwarzschild, by cutting and pasting pieces of that appropriately, because you see you have a hole here. So you can build things around, and in fact there is a metric which describe exactly this thing here, which can be written explicitly. I'm not writing the equations, but I give you the picture. It's very simple. The picture is the following. Let's do the simplest version. The simplest version is assuming that this is time symmetric. Is symmetric under time reversal around this line. Then it can be changed and modified to make this part different from this. But to start with, so let me just give the metric of this region here, outside sigma and including the black hole. Well, there is some time, which is the bouncing time. So let's say that the bouncing time is this one. There is some continuation into the black hole, some star that falls, where a star that falls in this picture is something like that. Okay, so you're outside the star that fall. There is a piece of horizon. The piece of horizon is this one. Okay, and the surface sigma cuts away a part of it, starting from a point here. So it cuts away something like that. So the geometry of this, you can take it to be the geometry of this part here. So this is a star. This is the boundary. So take this piece. Okay, so this is a star. And take it time reversal. And is this piece here. And glue it along this line. So you take this, you take a time reversal. You glue this with this, you open up this, this flap here and you put the quantum region inside. This can be done in equations, cleanly, has been done, and you get metric of the outside here. Okay? And you have a metric which depends only on two parameters. The result of the metric depends on two parameters. One is the mass of the Schwarzschild black hole, so the mass of this corpuscle here is a mass, which is the same all around. I mean, there's no Schwarzschild, there's no Hawking radiation here. And the other is the time that this passes. And there are many ways of computing this time. One possibility is to characterize it by saying where the horizon form and how much time passes between that, say, this time here, for instance, and the moment in which the transition happened. That's one characterization of time. There are other characterizations of time. But the point is that the external metric here can be explicitly given and have some ds, which depend explicitly on the mass and on the time. The mass is just the mass of the star. Okay? If you evolve, the classical theory doesn't say anything what's going to happen. It's a quantum theory that says how you're continuing. So the quantum theory should tell you what is the time it takes an object of mass m to go through this transition. Right? So the quantum theory should say something about this this process that depends on the mass and the time. So the geometry, both the intrinsic and geometry, we have it explicitly as a function of m and t. Which means at the end of the day, I'm going to compute an amplitude which depends on m and t. And how do I compute it? Well, I do a discretization of this surface. Let's do it. Let's do it for real. So let's look what is the shape of this surface. This is a four-dimensional picture. This is a two-dimensional. So this is a sphere, an S2. Right? It's a sort of a sphere that surrounds the black hole at the moment of the transition around the black hole. And this sigma here is the interior of the sphere. There's a ball inside this sphere. So I have a ball, okay, the interior of this S2, which is a past one and another future one. which are glued at the boundary, are glued here. Right, one inside and one outside. So let me discretize a ball. Well, one possibility is just to take the interior of the tetrahedron, but that's too rough as a discretization. Let's do it a little bit more refined, otherwise we can't compute anything. So let's pick a point and break this in 4 tetrahedra. So I have 4 tetrahedra here, 4 tetrahedra here, attached to one another, whose surface is attached to this one. Now the dual of this triangulation is very simple, because here the 4 tetrahedra attached to one another. Okay. So these are the 4 tetrahedra attached to one another, attached to the outside to 4 other attached to one another, attached to the upper one. So this is the gamma. Okay, it's 4 valent. It's a gamma. It's a graph, and is a discretization of sigma. Discretize sigma. This is the past, this is the future. 4 tetrahedra down, 4 tetrahedra up. And this S2 is the surface here, which is the boundary of this is just this 1, 2, 3, 4 triangles attached that separate the upper from the down. Good. So now I want this is a spin network. The graph of the spin network. So now I have the explicit metric, so I compute the metric of sigma, I can discretize and I have a discrete metric here. And so I explicitly have sizes of these triangles and angles, and I have everything. So I can write a coherent state corresponding to the metric that I get from the outside. It takes work, as Fabio knows very well, who has done this work. It takes a long work and painful and slow, but you can do it step by step. So you end up by writing a state in the Hilbert space of 1, 2, 3, 4, 8 nodes and whatever links they are. 12 plus 4, 16 or whatever. It's a state dependent explicitly on the geometry, so of M and T. And it depends on the extrinsic and intrinsic geometry, which I can compute. I compute the angle between the tetrahedra and so on and so forth. I just have to choose my surface wisely, so there's a lot of technicality. Once I have this state, I compute its amplitude, the amplitude of this state. And since the state depends on M and T, this is an amplitude that depends, I call it W. And how do you compute it? I have to put a two complex in between, a spin foam, and use the formulas. What is the two complex? I choose the simplest. And the simplest is a triangulation of the inside, and the simplest triangulation of the inside in the calculation that Marius and Fabio have been doing, they consider more general triangulation, but let me just mention the simplest, which is to break this in two simplices. One lower simplex and one upper simplex. The lower 4 simplex and the upper 4 simplex are joined by a tetrahedron. The lower one has 4 tetrahedra, is bounded by 4 tetrahedra. The upper one is bounded by 4 tetrahedra. So its boundary is exactly what I want. And so what is this triangulation? This spin foam? I have 2 vertices joined by an edge, tetrahedron, 4 edges up, 4 edges down, which end up into the 4 upper nodes and the 4 lower nodes, so that this sits on the boundary of that, right? 1, 2, 3, 4. This is the upper one. This is the lower one. And this sits at the bottom of that. Okay? So I have this explicitly. I have the amplitude corresponding to this explicitly is a bunch of integrals of SL2C, a bunch of integral of SO4, a bunch of Wigner matrices. So I suffer through trying to organize, and there's a lot of symmetries because all the areas are the same. And so I work all that. I exploit the symmetries. I exploit the scaling. I do some technical stuff. At the end of the day, I need a function of I compute a function of two variables. I cannot compute exactly. I compute it an approximation. I go to the large J limit because I still have, this is macroscopic, so this is large, but I don't want to, I want, in the large J limit, this should give zero amplitude. So I want to see before it goes to zero what happens here. And, oops, it's almost the end. So I get, this has been computed explicitly with this triangulation, and in fact with a set of triangulations more refined than this one as well. And in some approximation, we know that. In fact, this is the paper by Fabio D'Ambrosio and Mario Christodoulou, a couple of papers, one is out, one is coming, in which this calculation has been done. What does one extract from this? Well, the modulus square of this quantity is a probability, and it has to do with the probability of this transition happening for a mass m in a certain time. So there is a number of information that one can extract out of it, and this is requires some discussion, some physics. Let me give you the simplest of all of them. The probability itself, so the modulus square of this, turns out to be, and that's very credible, suppressed by a factor which is m squared over h bar g. I put the unit in, which tells me that for a macroscopic, this is a Planck mass. Let's call G, because if I put G is not downstairs, let's put H bar. So let's put M Planck. That's correct. So for a macroscopic object, in fact, there's a number here which they've computed, 1,832 or something like that. Yes. Which means that for a macroscopic black hole, this is definitely suppressed, right? Because this is a huge number, this is zero. So this, we see this expression. So the theory is saying, wait, this is not going to happen for a macroscopic black hole, at least in this approximation. Maybe better approximation might happen. But the theory is also tell this is going to happen for a black hole when it's small. If the black hole shrinks near to the Planck mass, this goes to 1. So this goes to a number for the 1. So you have no more suppression for this happen. So at the end of the black hole evaporation, this process is going to happen. Okay? And what comes on the other side, because this is the interesting thing, what comes to the other side is not what people usually draw, and you probably have seen in innumerable talks and pictures, that at the end of the black hole evaporation, the black hole disappears and there is nothing at all. But at the end of the black hole evaporation, there is a white hole with a huge inside, because this is a huge inside. So this picture, this usual picture, is completely wrong, because we have this future horizon and a lot of stuff which can still come out after the black hole has shrunk. So the theory tells us that there is a remnant, perhaps small, which is a white hole with a small size, but a long interior. And there is a lot of physics now being done with a small side and long interior. The transition itself might lead to some phenomenology. This white hole, this is my wild idea, could be one component of dark matter, and so on and so forth. So you see, not going into this, the actual calculation, detail of the physics, but you see how the full quantum gravitational theory works for studying a physical phenomenon. The idea being quantum gravitational events happen in some region. We surround this region with a surface. We compute, what are we computing? Morally, the functional integral on the geometry is inside, right? So inside there is not a fixed geometry. It would be an effective geometry, but the geometry is fluctuating wildly inside. There is a tunneling between the two, and the theory has all the machine for computing this transition amplitude. Good, so this is where we are. 20 hours to get to this point. And I think I can stop here.